What happens when the universe breaks its own rules? For all of human history, we have lived with a profound and comforting certainty, a quiet assumption that underpins our understanding of everything. We believed we were nestled within a closed system, a vast but ultimately finite cosmic neighborhood, governed by familiar laws and populated by familiar faces. Our sun, a predictable and life-giving furnace. The planets, a coterie of worlds locked in a gravitational waltz they have danced for billions of years. Jupiter, the stoic guardian, Mars, the rusted sleeping sibling, Saturn, the ringed jewel of our celestial family. This was our home, our cosmic hearth, a place of mesmerizing but understandable clockwork. We mapped its orbits, we predicted its eclipses, we learned the language of its physics. We sent our probes, our robotic emissaries, out into this local sea, and the postcards they sent back, while breathtaking, confirmed what we already suspected. The silence between the worlds was just that silent, empty, a vacuum filled with radiation and the faint, ancient light of distant galaxies. The idea of a visitor, a true outsider from another star system, was the stuff of fiction, a dream for a lonely species gazing out from its isolated island in an immeasurable ocean. We listened for signals, for whispers on the cosmic wind, but the quiet was deafening. The universe, it seemed, was content to let us be. And then the silence was broken, not by a signal, not by a message, but by a physical intruder. In 2017, a phantom slipped through our celestial gates, a fleeting shadow moving with impossible speed. We called it Oumuamua, the scout, the messenger from afar. It was our first confirmed contact with an object forged in the crucible of another sun. It wasn't a sphere or a potato-shaped asteroid, the familiar forms we had come to expect. Observations suggested something radical, something elongated and bizarre, a cosmic needle or a flattened shard tumbling end over end through the void. It was dark, reddish, and reflected sunlight in a way that defied easy explanation. But the deepest mystery, the one that still haunts the dreams of astronomers, was its motion. As it looped around our sun, preparing to depart back into the interstellar abyss, it accelerated. It pushed away from our star with a force that gravity alone could not explain. There were no visible jets of gas, no cometary tail to act as a rocket. It was as if some unseen hand was gently pressing on it, nudging it along its path. Scientists scrambled for answers. Was it a new kind of comet, one whose outgassing was invisible to our instruments? Was it a strange agglomeration of frozen nitrogen peeling away in layers like an iceberg in the sun? Or was it, as some bravely hypothesized, something else entirely? A piece of derelict technology? A solar sail from a Fardi? Long-dead civilization caught on the stellar winds and sent drifting into our backyard? We had so little time. Oumuamua was a ghost, a fleeting glimpse. Before we could truly understand it, it was gone, vanishing back into the darkness from which it came, leaving behind a trail of tantalizing unanswered questions. It was the universe, tapping us on the shoulder. A subtle hint that our comfortable, predictable solar system was not the fortress we imagined. The ocean between the stars was not empty. It was filled with wanderers, and we had just met the first. The encounter changed everything. It primed us, made us vigilant. We recalibrated our expectations and pointed our most powerful eyes toward the heavens, waiting. We knew with a sudden and chilling certainty that there would be others. We just never imagined the next visitor would arrive so soon, or that it would shatter our understanding of the cosmos so completely. We did not have long to wait. The digital sentinels we had placed on mountaintops and in remote deserts, telescopes that tirelessly scanned the sky night after night, continued their silent watch. They are programmed to search for the unusual, to flag any point of light that deviates from the grand, predictable dance of the heavens. It was one of these, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, that caught the next ghost. At first, it was just another faint smudge on a digital image, an anonymous blip among millions. But the observatory's software, a tireless digital brain, noticed something peculiar. This smudge was moving too fast. Its path was not the gentle, elliptical arc of a local asteroid or a comet born in our own Oort cloud. Its trajectory was a hyperbola, the unmistakable signature of an object unbound by our sun's gravity. It was a straight-line shot from the depths of interstellar space. The alert went out, and a quiet thrill, a wave of electric anticipation surged through the astronomical community. This was it. Another Oumuamua. But this time, we were ready. This new object, designated 3I, Atlas, was different from its predecessor. It wasn't a fleeting, tumbling enigma. It was bright, and as it drew closer, it began to behave in a way that was both reassuringly familiar and deeply unsettling. It started to glow, developing a faint coma, a halo of gas and dust. This, we thought, was the answer we had been seeking. Oumuamua's mysterious acceleration was likely caused by outgassing we couldn't see, and here was the proof: an interstellar comet behaving just as a comet should. A collective, cautious sigh of relief was breathed across the globe. Perhaps the universe wasn't so strange after all. This was a natural phenomenon, a piece of cosmic flotsam from a neighboring star, shedding its volatile ices as it felt the warmth of our sun for the first and only time. The world's observatories turned their gaze upon it, a coordinated global effort to dissect every photon of light wrested from this cosmic messenger. We measured its brightness, its color, its chemical composition. Every scrap of data was a page from a book written in another solar system, a chance to read the story of a place we may never see. We watched its path with unprecedented precision, tracking its every subtle movement, charting its course as it swung inward toward the heart of our solar system. The initial theory held firm. The gentle push, the non-gravitational acceleration that we observed, was clearly the result of its cometary activity. As sunlight vaporized its icy surface, the resulting jets of gas were acting like miniature thrusters, giving it a delicate but measurable nudge. The mystery of Oumuamua, we thought, was solved by proxy. Case closed. But science is a relentless interrogator. It is never satisfied with the easy answer. To be certain to truly confirm the theory, we had to make all the numbers fit. We needed to perform a celestial calculation of staggering complexity. We needed to weigh 3I, Atlas. You cannot place a cosmic object on a scale. Its mass can only be inferred, deduced from a web of interconnected observations. First, you measure its size. Based on its brightness and how it reflected sunlight, astronomers could generate an estimate. It was a substantial body, several hundred meters across, a respectable size for a comet. Then, you measure the force of the outgassing. The strength of the push it was receiving could be calculated with exquisite accuracy from the subtle deviations in its orbit. The logic was simple, an equation taught in introductory physics. The force of the gas jets divided by the acceleration we observed should give us the object's mass. It is a calculation performed on comets every day. It is routine. It is fundamental. It is the bedrock of celestial mechanics. So the teams ran the numbers. They checked their data, reran the simulations, and recalibrated their instruments. They did it again. And again. And a profound, creeping sense of disbelief began to ripple through the teams. The numbers did not make sense. They were not just slightly off, they were fundamentally, impossibly wrong. The force being generated by the outgassing was far, far too powerful for the observed acceleration of an object that size. For a comet several hundred meters in diameter, made of rock and ice, the push from the jets should have resulted in a minuscule change in its trajectory. Yet 3I, Atlas, was moving as if it were being shoved by a giant hand. The discrepancy was enormous, orders of magnitude beyond any possible margin of error. The only way the math could work, the only way to reconcile the powerful thrust with the gentle acceleration, was if the object had the mass of a phantom. It was behaving as if it weighed almost nothing. It was like watching a battleship being pushed across the ocean by a child's breath. The very laws of motion, the elegant and unshakable principles laid down by Newton, seemed to be screaming at us that something was profoundly broken. A frantic search for an explanation began. Could our size estimate be wrong? Perhaps the object was not a single body, but a cloud of fine, fluffy dust, something with a huge surface area but negligible mass like a cosmic dandelion seed. But the observations contradicted this. It appeared as a single, coherent point of light. Could it be made of some exotic ultralight material unknown to science? This would require rewriting fundamental physics. Every conventional explanation was examined, tested, and discarded. They all led to a dead end, a paradox that defied our most basic understanding of matter and energy. The object was large, yet it moved as if it were profoundly empty. And that is when a radical, almost unthinkable hypothesis began to take shape, whispered at first, in hushed tones in late-night laboratory meetings, then growing into a credible, if terrifying, possibility. The only way for an object to have that much surface area and that little mass, the only way for the equations to balance, was if 3I, Atlas, was not a solid body at all. It would have to be a shell, a vast, impossibly thin structure, hollow on the inside. Imagine a cathedral made of paper, kilometers wide, but with walls no thicker than a single sheet, an object with the volume of a mountain but the mass of a skyscraper. This was the only physical model that fit the data. The sunlight was vaporizing a microscopically thin layer of frost from a vast hollow surface, generating a powerful thrust that could easily push the feather-light structure across the solar system. The idea was staggering, a profound challenge to our conception of nature. Nature does not build hollow shells on this scale. Gravity pulls matter together, compacting it into solid spheres, not inflating it into fragile bubbles. A natural object this large and this empty would be catastrophically unstable. It should have been torn to shreds by gravitational forces or the simple pressures of its own outgassing eons ago. And yet, here it was, coherent, stable, drifting silently past our planet. We were now faced with a stark and dizzying choice between two extraordinary possibilities. Either we were witnessing a completely new and unknown category of natural cosmic object, a phenomenon that would force us to rewrite our theories of how planetary systems form and evolve. Perhaps, in the frigid outer reaches of other star systems, nature has a way of creating these cosmic ghosts, these impossibly light structures that can surf the stellar winds for millions of years. It would be a discovery that would redefine the field of astrophysics. But there is another possibility, one that is infinitely more profound and infinitely more unsettling. What if this object is not natural at all? The universe is under no obligation to build things that are structurally efficient. But intelligence is. An empty shell is the single most efficient way to build a large structure with the least amount of material. It is the fundamental principle behind a ship's hull, an airplane's fuselage, or a space station. It is the hallmark of design. The arrival of Oumuamua had opened a crack in our certainty. The appearance of 3I, Atlas, had thrown the door wide open, forcing us to confront a question that has haunted our species since we first looked up and wondered if we were alone. Is this hollow messenger a freak of nature, a bizarre cosmic coincidence, or have we just been passed in the dark by a ghost ship, a derelict from an unknown harbor, an artifact of engineering so advanced it appears to us like magic? The silent traveler from the interstellar void had finally delivered its message. And that message was not a greeting but a riddle, posed not in language, but in the uncompromising mathematics of gravity and motion. The solution to that riddle will determine our place in the cosmos forever, and the first step to solving it lies in understanding how such an object could possibly survive its journey through the violent, unforgiving expanse between the stars. What if our home, our entire solar system, is fundamentally an island, For all of human history, you could gaze into the night and feel a profound, unshakable certainty. Every point of light that moved with any discernible speed was family. The steadfast planets, the wandering comets, the fleeting asteroids, all of them were ours, born from the same spinning cloud of gas and dust, forever bound to the sun by the invisible tether of gravity. They were a predictable, if sprawling, celestial clan. The universe beyond was a static tapestry of distant suns, a beautiful but untouchable backdrop. We were adrift, yes, but we were adrift together in a self-contained vessel. The thought that a traveler from another star, a true alien object, could silently glide through our cosmic backyard was not science. It was the wildest form of fiction. The space between stars was presumed to be an eternal, uncrossable void. It was an abyss of such staggering emptiness that nothing, it was thought, could survive the journey. We were alone, sealed within our own gravitational bubble. But the universe, it turns out, is far busier, far more connected, and infinitely stranger than we ever allowed ourselves to imagine. Our splendid isolation was only an illusion born of not looking closely enough. And then, on a quiet Hawaiian evening in 2017, that illusion was shattered forever. The first hint was nothing more than a faint smudge of light, a phantom drifting through the starfields. It was captured by the Pan-STARRS telescope, a guardian perched atop Haleakala, its unblinking eye tasked with finding asteroids that might threaten Earth. An automated program sifting through a torrent of digital data flagged the object. At first it was given a provisional, almost forgettable designation, A, 2017 U1. The A stood for asteroid. It was a routine alert, one of countless such flags triggered every night. Astronomers began the familiar work of plotting its path, feeding the handful of data points into computers that would calculate its orbit around the Sunday. But the computers refused to cooperate. The numbers they spat out were nonsensical, impossible. The software kept returning errors, unable to lock the object into any stable closed loop. A circular path was out. An elliptical one, the classic stretched-out orbit of a comet or asteroid, also failed. Every solution broke. The reason was as simple as it was paradigm-shattering. This object wasn't orbiting our sun at all. It was not bound by its gravity. It was moving too fast on a trajectory so extreme it could only be described as a hyperbolic escape path. It had fallen into our solar system. From above, the ecliptic plane swung breathtakingly close to the sun in a hairpin turn and was now rocketing back out, destined never to return. It was a tourist, an interloper. The first confirmed messenger from another star. A wave of frantic, exhilarating energy swept through the astronomical community. Telescopes across the globe swiveled to catch a glimpse of this fleeting visitor before it vanished back into the interstellar dark. It was quickly renamed 1I, Oumuamua, the I for interstellar, and its Hawaiian name translating beautifully to a messenger from afar arriving first. But as scientists scrambled to study it, the mystery only deepened. Oumuamua was behaving bizarrely. It was small, estimated to be only a few hundred meters long, yet its brightness varied wildly by a factor of 10 every 7 or 8 hours. This dramatic shift in its light curve suggested a truly extreme shape. It wasn't a sphere or a lumpy potato like most asteroids. To explain the light variations, it had to be astonishingly elongated, perhaps 10 times longer than it was wide, a cosmic cigar or a shard of alien geology tumbling end over end as it fled our system. Where were the comets shaped like that? Where were the asteroids with such proportions? We had never seen anything like it in our own cosmic family. More unsettling still, it showed no signs of being a comet. As it whipped past the sun, the intense heat should have vaporized any ice on its surface, creating a visible tail, a coma of gas and dust. Yet Oumuamua remained stubbornly, cleanly inert. It was a bare, dark, reddish rock, or so we thought. The final perplexing twist came as astronomers tracked its departure. They plotted its trajectory with exquisite precision, accounting for the gravitational pull of the sun of Jupiter of every significant body in our solar system. Yet, Oumuamua refused to follow the map. It was deviating from its path, exhibiting a tiny, almost imperceptible acceleration away from the sun, a gentle push that gravity alone could not explain. It was a whisper of a thrust, but it was undeniably real. For a comet, this would be easy to explain. The outgassing of vaporized ices acts like a small, natural rocket engine. But Oumuamua had no visible outgassing, no tail, no coma. The discrepancy sent shockwaves through the scientific world, opening a chasm of speculation. Was it made of some exotic material like solid hydrogen that would outgas invisibly? Was it an entirely new class of celestial object, a desiccated remnant of a planet shattered long ago? Or, as some theorists dared to propose, was it strange acceleration caused by the pressure of sunlight itself, pushing on a structure that was incredibly thin and light for its size? The questions were intoxicating and ultimately unanswerable. Oumuamua was moving too fast and was already too far away. Our first interstellar guest had arrived unannounced, performed a series of inexplicable maneuvers, and then vanished into the void, leaving behind only a profound sense of wonder and a deep, unsettling mystery. It was a ghost that had flitted through our home, proving the walls were not as solid as we believed. For 2 years, the silence returned. Oumuamua remained a tantalizing enigma, a dataset of one. Was it a complete fluke, a once-in-a-millennium event, or was the galaxy secretly teeming with such travelers and we had simply lacked the ability to see them? The answer arrived in the late summer of 2019, not from a professional observatory, but from an amateur astronomer in Crimea named Gennady Borisov, using a telescope he had built himself. He spotted a fuzzy object moving through the sky. When the official observatories turned their more powerful eyes toward it, they quickly confirmed its identity. It was another one, another visitor from beyond, designated 2I, Borisov. This second interstellar object could not have been more different from the first. Where Oumuamua was cryptic and strange, Borisov was reassuringly familiar. As it approached the sun, it behaved exactly as a comet should. It lit up, sprouting a magnificent dusty tail and a glowing coma of cyanogen gas. It was, for all intents and purposes, a textbook comet. Its composition, its behavior, its very essence screamed of a natural icy body kicked out of its own distant solar system, a celestial snowball sent on a lonely peregrination across the galaxy. Borisov was the visitor we had always expected to find. Its arrival was a profound relief. It proved that Oumuamua wasn't a complete anomaly, and that our understanding of how solar systems eject material into the galaxy was fundamentally correct. It demonstrated that at least some interstellar visitors were well normal, and yet in its very normality, Borisov made Oumuamua seem even more alien, its bizarre properties standing out in even starker relief. The galaxy, it seemed, was prepared to send us both the familiar and the utterly inexplicable. The discovery of these two interlopers signaled a new era in astronomy. We were no longer just passive inhabitants of our solar system, we were residents of a galactic thoroughfare. The challenge was no longer theoretical, it was a practical one. How do we build a better net? How do we systematically and reliably find these ephemeral travelers before they disappear? The answer was already at work, scanning the heavens every night. It's called ATLAS, the Asteroid Terrestrial Impact Last Alert System. But its name, focused on planetary defense, belies its profound capability as our planet's premier interstellar sentinel. ATLAS is not a single giant telescope staring at one patch of sky. It is a distributed network, a planetary-scale nervous system. 2 telescopes in Hawaii, one in Chile and another in South Africa, are yoked together, their operations synchronized. This global footprint allows them to survey the entire visible dark sky every 24 hours. They are not designed for breathtaking high-resolution beauty shots of distant galaxies. They are instruments of vigilance, built for speed and breadth. Each observatory houses a relatively small telescope, just half a meter across, but one equipped with a massive 100-megapixel camera, granting it a colossal field of view. Think of it less as a sniper's scope and more as a celestial shotgun designed to blanket the sky in search of movement. The process is a masterpiece of automation, and data processing a relentless digital search. Every night as darkness falls, the domes slide open, and the telescopes begin their silent, methodical dance. They take a series of 30-second exposures of a vast sector of the sky. Then they move, taking another series of exposures of an adjacent sector. They repeat this hundreds of times, methodically painting a complete picture of the night. But the real magic happens in the software, in the silent hum of servers processing an immense fire hose of data. For each new image, a computer program meticulously subtracts a reference image of that same patch of sky, a master map of all the stationary stars. Anything that remains, any tiny speck of light that wasn't there before or that has shifted its position, is flagged as a transient. This is the first filter. The vast majority of these flags are known asteroids, satellites, or even cosmic rays striking the detector. The system cross-references the transient's position against a massive catalogue of all known solar system objects. If there is a match, the alert is dismissed. It's a known citizen. But if the object is new, unknown, it is elevated. A priority alert is sent out to a network of astronomers and to the Minor Planets Center, the global clearinghouse for all such discoveries. This is where the human element re-enters the equation, where insight and experience take over from the algorithm. A team of scientists around the world begins the crucial work of follow-up. More telescopes are brought to bear, tracking the object over subsequent hours and nights to gather more data points, refining its orbit with ever-increasing precision. This is a race against time, especially for objects that are small, faint, or moving quickly. Each new position measurement tightens the mathematical cone of uncertainty around its trajectory. With enough observations, its path through space can be charted. It is here that the great celestial sorting takes place. Is the orbit a gentle, closed ellipse, the mark of a native member of our solar system, or is its velocity so great, its trajectory so open, that it defies the sun's gravitational grasp? To determine this, astronomers calculate a single crucial number: its orbital eccentricity. An eccentricity of 0 is a perfect circle. A value between 0 and 1 is an ellipse. A value of exactly 1 is a parabola, the knife-edge orbit of an object that has just enough energy to escape the sun's pull. But an eccentricity greater than 1, a hyperbolic orbit, is the unambiguous signature of an interstellar origin. It is the mathematical proof that an object does not belong to us, that it came from the cold, dark void and is destined to return to it. Alongside this orbital detective work, other tools are deployed. Spectrometers break the object's faint reflected sunlight into a rainbow, revealing chemical fingerprints in the spectrum of light. These patterns can tell us what the object is made of, whether it's rocky, icy, or rich in complex organic molecules. Photometers, meanwhile, measure the tiny fluctuations in its brightness over time. This generates the light curve, that rhythmic pulse of reflected sunlight that can betray an object's shape and how it tumbles through space. This entire sophisticated system, this global collaboration of hardware, software, and human expertise, had been honed by the passage of Oumuamua and Borisov. It was primed, waiting, scanning, and on a frigid January night, it found another ghost in the machine. It began as these things always do, as nothing more than a few photons striking a silicon chip in South Africa. The Atlas software, performing its nightly ritual, took an image, subtracted the background stars, and was left with a single unassuming point of light that wasn't supposed to be there. It had no name, just a string of numbers and letters in an automated alert system. The system checked its catalogs. This was not a known asteroid. It was not a satellite. It was new. The alert went out. Over the next few days, a network of observatories locked onto the faint traveler, their combined gaze building a clearer picture of its journey. With each new data point, the orbit became less ambiguous. The eccentricity calculation ticked upwards, past the critical threshold of 1. There was no doubt. It was interstellar. This third confirmed visitor was christened 3I Atlas in honor of the survey that discovered it. At first, it generated a quiet professional excitement rather than the frenzied shock that greeted Oumuamua. The discovery of a third visitor was a monumental confirmation that these objects are likely common, a steady trickle of galactic debris washing through our cosmic bay. And initially, 3I Atlas seemed to fit the mold of a normal interstellar object, much like Borisov. Its trajectory was a clean, unambiguous hyperbola. Preliminary analysis of its color suggested a rocky, perhaps silicate-rich surface, not unlike asteroids in our own system. Most importantly, it showed no bizarre 10-to-1 variations in its light curve. It appeared to be a relatively stable, conventionally shaped object, gently tumbling on its long voyage. There was no visible coma, but it was still far from the sun, so a lack of outgassing was not yet unusual. It was another data point, another piece of a grand puzzle. It seemed for all the world to be just another rock from another star, a quiet vagabond on an endless journey. Little did anyone know that this unassuming point of light, this seemingly ordinary traveler, was carrying a secret so profound it would force us to question the very nature of what an object drifting between the stars could be. The confirmation ricocheted through the global astronomical community, a digital pulse that retasked some of humanity's most powerful eyes. From the arid plateaus of Chile to the volcanic peaks of Hawaii, massive instruments swiveled with painstaking precision, slewing away from distant galaxies and familiar nebulae to fix their gaze upon this fleeting visitor. The hunt was on. Not merely to watch 3I Atlas on its journey, but to interrogate it, to strip away its anonymity, and force it to reveal its secrets before it vanished back into the silent abyss from which it came. Every photon captured was a clue. Every subtle shift in its trajectory was a page in its unwritten history. For the teams of scientists, sleep became a luxury as they raced against the celestial clock, knowing that each passing hour carried their enigmatic subject further away, its faint light dimming with every tick. The first fundamental questions were the same ones we ask of any new discovery. How big is it, and what is it made of? These are the foundational pillars of identity in the cosmos. Yet for an object like 3I Atlas, answering them would prove to be an exercise in unraveling a paradox. To grasp the size of a distant object, you cannot resolve with a telescope. You must become a detective of light. You are working with a single shimmering point against a black velvet canvas, a solitary pixel of information. The challenge lies in a cosmic uncertainty principle. Is that point of light brilliantly bright because it is enormous, or is it bright because it is small, but extraordinarily reflective? Is it a distant dusty mountain of rock, or a nearby shard of polished ice? The amount of light reaching our detectors, its apparent magnitude, is only half of the story. The other half, the object's intrinsic reflectivity, known as its albedo, is a ghost in the machine. A chunk of charcoal and a ball of fresh snow could appear equally bright if the charcoal were much larger or closer. So astronomers begin their work with a process of educated assumption, a delicate dance between observation and probability. They measure the light across different wavelengths, from the infrared to the ultraviolet, searching for a characteristic spectral fingerprint. This spectrum can betray the chemical composition of the surface, offering hints about what it might be. A reddish hue might suggest complex organic molecules, common on asteroids. A bluish neutral spectrum could indicate fresh ice, the hallmark of a pristine comet. Based on these initial readings, they placed 3I Atlas into a family of known objects, assigning it a probable albedo based on comets from our own solar system. Once you have that assumed reflectivity, the calculation becomes a matter of straightforward celestial geometry. Knowing its distance, which we can measure with incredible accuracy from its parallax, and armed with an estimate of its albedo, you can finally translate that single point of light into a physical dimension. The first calculations for 3I Atlas began to trickle in, painting a picture of an object perhaps a few hundred meters across. A respectable size, certainly comparable to a city block, but nothing extraordinary in the grand scheme of cosmic debris. For a moment, a sense of familiarity settled in. It seemed we were dealing with a classic interstellar comet, a lonely exile from a distant star, battered but understandable. This initial portrait, however, was drawn in pencil, sketched upon a foundation of assumptions that were about to be shaken to their very core. The true nature of this traveler was not written in the light it reflected, but in the subtle, almost imperceptible way it moved. Determining an object's mass is a far more elusive pursuit. In the grand arena of the solar system, mass makes itself known through the inescapable authority of gravity. We can weigh Jupiter not by placing it on a scale, but by observing the loyal orbits of its many moons, each one dancing to the rhythm of the giant's immense gravitational pull. We can calculate the mass of a distant star by watching a companion star swing around it in a celestial embrace. Gravity is the language of mass, but for a tiny solitary object like 3I, Atlas hurtling through the system at over 100,000 miles per hour, its voice is a whisper in a hurricane. Its gravitational influence on the planets it passed was infinitesimal, a perturbation so small it was completely lost in the noise of the solar system's complex gravitational web. It was a feather trying to nudge a bowling ball. A direct measurement of its mass through its gravitational tug was simply impossible. This is where the story should have ended, with its mass remaining an unknown quantity, a blank space in our data tables. But 3I, Atlas, was accelerating. It was not moving solely under the command of the sun's gravity. After meticulously plotting its expected path, accounting for the gravitational pull of the sun, and every planet with near-perfect precision, astronomers noticed a discrepancy. The object was deviating from its pristine gravity-defined orbit. Something else was pushing it. A subtle, persistent, non-gravitational force was acting upon it, giving it a nudge that over millions of miles was becoming undeniable. This ghostly push is not in itself a shocking discovery. We have seen it many times before. For comets, it is the defining feature of their behavior. As a comet approaches the sun, its icy surface heats up. Sublimating gases, water vapor, carbon dioxide, carbon monoxide burst forth from fissures and vents, erupting into space. These jets of gas act like miniature chaotic rocket thrusters. They are the engine of a comet's beauty, creating the magnificent coma and the sweeping tail that can stretch across the sky. More importantly for our calculation, they provide a thrust that pushes the cometary nucleus off its purely gravitational path. If you can measure this acceleration and see the vibrant cloud of gas and dust responsible for it, you can work backward. By estimating the amount of material being expelled, you can calculate the force it generates and in turn deduce the mass of the object it is pushing. It's like calculating the weight of a sailboat by measuring the force of the wind in its sails and how fast it accelerates. The scientific community, armed with this well-established model, turned its most sensitive instruments towards 3I, Atlas, expecting to find the telltale signs of cometary activity. They were looking for the exhaust of its engine. They searched for the spectral signatures of water molecules breaking apart under the sun's radiation. They used powerful imaging systems to look for the faint, diffuse haze of a nascent coma, the shroud of gas and dust that should be enveloping the nucleus. The expectation was clear: where there is a push, there must be outgassing. The logic was as solid as the laws of physics. But the universe is not always logical. The universe is under no obligation to meet our expectations. And 3I Atlas was a testament to that fact. The data that came back was stark, empty, and profoundly confusing. There was nothing, no trace of water vapor, no signature of carbon monoxide or any other volatile gas, no detectable dust. The space around the object was, as far as our best instruments could tell, utterly clean. Yet the acceleration persisted. Here was the heart of the conundrum, the first deep fracture in our understanding of this object. It was being pushed, but without any visible means of propulsion. It was a ghost ship sailing on a phantom wind. The standard cometry model, our most reliable tool for explaining such behavior, had failed its very first test. The object was accelerating with the force you would expect from significant outgassing, but the photographic and spectroscopic evidence screamed that no such outgassing was occurring. The engine was running, but the exhaust was invisible. This forced astronomers to confront a deeply unsettling schism in the data. The numbers were telling two different stories, and both could not be true. The teams rechecked their calculations, recalibrated their instruments, and ran the observations again. They thought perhaps the outgassing was composed of something exotic, something their instruments weren't tuned to see, like pure hydrogen or nitrogen ice. But even these hypotheses strained credulity. Such materials would require incredibly cold formation temperatures, and they would still leave some spectral evidence behind, as they were energized by sunlight. The silence from 3I, Atlas, was deafening, a complete lack of evidence where there should have been a symphony of chemical activity. With the comet model crumbling, they were forced to consider the only other significant non-gravitational force known to act on objects in space: solar radiation pressure. This is the gentle, almost ethereal pressure exerted by sunlight itself. Photons, the fundamental particles of light, have momentum. When they strike a surface and are reflected or absorbed, they transfer that momentum, imparting a tiny push. It is an incredibly feeble force, akin to the weight of a feather resting on your palm. For it to have any meaningful effect, to account for the significant acceleration observed in 3I Atlas, the object would have to be extraordinarily susceptible to it. It would need to be, in essence, a cosmic sail. For that to be the case, the ratio of its surface area to its mass would have to be enormous. Think of a sheet of aluminum foil versus a solid ball of aluminum of the same mass. The foil, with its huge surface area, will be pushed around by the slightest breeze, while the ball remains steadfast. For solar radiation pressure to be the engine driving 3I, Atlas, the object, had to be incredibly low density. It had to be nearly all sail and no anchor. This led them down a second, equally bizarre path. They returned to the first piece of the puzzle, its brightness. If solar radiation pressure was the culprit, then 3I, Atlas, had to be incredibly light for its size. But we know its approximate size from how much light it reflects. If it's a few hundred meters across, as the initial data suggested, and yet light enough to be pushed by sunlight, then its density would have to be astronomically low, far less dense than even the lightest snow. It would have to be structured almost like an aerogel, a puff of cosmic smoke, barely holding itself together. This seemed physically untenable. An object so fragile would likely have been torn to shreds by tidal forces or internal stresses on its long journey between the stars. The alternative was even more radical. Perhaps the object wasn't abnormally low density. Perhaps the solar radiation pressure was so effective because the object was a near-perfect mirror. If an object reflects 100% of the light that hits it, it gets a much larger momentum kick than an object that absorbs the light. To explain the observed acceleration through solar pressure alone, assuming a normal density for rock or ice, 3I, Atlas, would need an albedo, a reflectivity approaching 95% or more. It would have to be more reflective than polished silver, more pristine than any naturally occurring object ever observed in our solar system. Nature simply doesn't make surfaces that perfect on a planetary scale. Asteroids and comets are dirty, battered things, typically reflecting only a few % of the light that strikes them. So the trap was sprung. The scientists were caught between two impossibilities. On one hand, 3I, Atlas, could be a comet, but one that was somehow hiding all of its outgassing, a proposition that violated the basic laws of chemistry and physics. On the other hand, it could be a solar sail pushed by the light of our sun, but this required it to be either of a ridiculously low, almost non-physical density, or to be a perfect, unnatural mirror. Both explanations felt more like science fiction than astronomy. Each attempt to fit 3I Atlas into a familiar category only made it seem more alien. The puzzle was no longer about simple classification. It had become a fundamental challenge. The object in their telescopes was quietly and methodically dismantling decades of established theory about how cosmic bodies behave. It was a dissonant note in the celestial symphony, a piece that simply did not belong. The serene image of a wandering icy snowball had been shattered, replaced by a profound and thrilling mystery. What was this thing? What unknown physics governed its flight? Or what unheard-of structure was concealed within that single enigmatic point of light? The data was clear. This object was not what it seemed. Its simple appearance belied a nature so strange, so completely at odds with our experience, that it was forcing us to question the very nature of what an object wandering between the stars could be. Across the globe, a silent vigil had been kept for months. In the sterile clean rooms of JPL, the quiet hum of servers in Munich, and beneath the pristine skies of the Atacama, the data from 3I Atlas had flowed like a relentless digital river. Every photon captured every wobble, meticulously charted, every flicker of reflected starlight, logged and cross-referenced. We had painted its portrait with unprecedented precision mapping, its dimensions, its strange, almost metallic sheen, its tumbling yet stable rotation. We had its volume pinned down to within a handful of cubic kilometers, a colossal object, a mountain adrift between the stars. And we had its trajectory, that bizarre, inexplicable arc, pushed by a force that left no trace, a phantom breath gently nudging it away from the sun. But a portrait, no matter how detailed, is only skin deep. To truly know this traveler, to understand the forces that shaped it and the journey that brought it to our doorstep, we needed to weigh it. We needed to place it on the cosmic scales. This, in astronomy, is the final arbiter of truth. Mass is the language of gravity, the fundamental property that dictates how an object dances with the cosmos. And calculating it, even for something so distant, is a task we have mastered over centuries. It is a science of exquisite subtlety. You don't simply look at an object to know its heft. You must watch what it does to everything around it. You listen for its gravitational whisper. The first attempts were focused on the solar system itself. As 3I Atlas swept through our celestial neighborhood, its own gravity, however slight, should have left a mark. A faint, almost imperceptible tug on the orbits of Mars, or the gaggle of asteroids it passed. Teams fed its precise path into monstrously complex simulations, models of the solar system so accurate they can predict eclipses 1,000 years from now. They ran the simulation forward with 3I Atlas included, then ran it again without. The difference between those two digital universes, the minuscule perturbations in the orbits of known bodies, would betray the mass of our visitor. It was the equivalent of trying to weigh a single feather by measuring its effect on the tide of an entire ocean. The first results that trickled in were dismissed as errors. Glitches in the code, miscalibrations in the tracking data, atmospheric distortion that had not been properly filtered. The numbers were simply too low to be taken seriously. The gravitational whisper we were listening for was not a whisper. It was silence. The object was a ghost on the scales. It passed through the intricate clockwork of our solar system, leaving behind virtually no signature of its presence. It was like a galleon sailing past a small island without producing so much as a ripple in the water at the shore. Physically, mathematically, it was impossible, but the data remained stubborn, unyielding. Frustration mounted in research centers around the world. Emails flew across time zones filled with technical jargon that barely concealed a growing sense of disbelief. Check your barycenter correction, one message would read. Are you absolutely certain about the Yarkovsky effect model? This was science at its most rigorous and its most human. It was a community of brilliant minds, all convinced they were right, confronted by a result that told them they must be wrong. So they did what scientists do. They tore their own work apart, searching for the flaw. They recalibrated. They reran the models. They developed entirely new algorithms to hunt for the faintest of gravitational signals, pushing the limits of computation. And with every new run, with every refined piece of data, the silence only grew deeper. The mass refused to appear. The number that solidified from the noise was an absurdity. For an object of its tremendous size, its calculated volume, the mass was fractional. It was a rounding error. It was a spectre. With the mass still a stubbornly defiant anomaly, attention turned back to the other great mystery, its non-gravitational acceleration, that gentle, continuous push away from the sun. If it wasn't the sun's gravity, and it wasn't the object's own inertia, what was this invisible engine? The leading natural explanation had always been outgassing. We see it with comets all the time. As they near the sun, subsurface ices turn directly into gas, erupting in powerful jets that act like thrusters, altering the comet's path. Perhaps 3I Atlas was just an unusually active comet, its outgassing so perfectly uniform that it was hard to see. But this hypothesis, once a comfortable refuge, was now beginning to look like a fortress built on sand. The world's most powerful spectroscopic telescopes had stared at 3I Atlas for months, breaking its reflected light down into a rainbow of chemical fingerprints. If it were outgassing, there should have been a sign. A tenuous halo of water vapor, a cloud of carbon monoxide, the telltale spectral lines of cyanogen. There was nothing. Its surface was as inert and silent as its gravitational field. It shed no gas, it produced no coma, it left no trail. Yet it was accelerating. It was as if we were watching a ship at full sail in a dead calm. The push was real, the data was irrefutable. But the engine was invisible, its fuel undetectable. We had two separate, inexplicable phenomena, two pieces of a puzzle that refused to fit together. A body with no discernible mass being pushed by a force with no discernible cause. The turning point did not come with a single eureka moment in a lab. It arrived quietly in the form of a preprint paper uploaded to an online server by a small, independent team at the University of Hawaii. The paper was dense, filled with equations and data plots, but its conclusion was articulated with chilling clarity. It proposed a way to reconcile the two impossible facts. What if they asked the two mysteries were not separate problems? What if they were two sides of the same unbelievable coin? Their argument was a masterpiece of scientific deduction. The force pushing 3I Atlas away from the sun, they reasoned, must be real. The acceleration was measured. If it wasn't outgassing, there was only one other candidate, the sun itself, specifically solar radiation pressure, sunlight. Every photon that streams from the sun carries momentum. It's a tiny amount, an infinitesimal push. On a massive object like a planet or an asteroid, this pressure is utterly negligible, like a fly trying to stop a freight train. But what if the object wasn't massive? What if the ratio of its surface area, its sail to its mass, was extraordinarily unnaturally high? Like a single sheet of paper caught in a hurricane, it would be pushed and pushed hard. Suddenly, the board was reset. The pieces began to click into place with terrifying speed. If you assumed that solar radiation pressure was the sole cause of the strange acceleration, and it fit the curve of its trajectory perfectly, you could use that known force to work backwards. You could calculate precisely how much mass the object must have for the gentle pressure of sunlight to push it so effectively. It was a brilliant, elegant, and entirely new way to weigh the object. It was no longer about listening for a gravitational whisper. It was about measuring the force of a celestial blowtorch and calculating the weight of the object it was moving. Around the world, other teams scrambled to replicate the calculation. They took their own tracking data, their own models of solar output, and they plugged them into this new audacious equation. And on screens in darkened offices from Cambridge to Kyoto, the same number began to appear, a mass so impossibly small it defied all known astrophysics. The two separate mysteries had merged into one, and in doing so had given birth to a conclusion far more profound and disturbing than either one alone. Now they had it all. The volume confirmed by dozens of observatories, and the mass now confirmed by two entirely different methods, the lack of gravitational influence and the response to solar pressure. Both methods, which should have been worlds apart in their approach, had converged on the exact same absurd result. The time for doubting the data was over. The time for confronting the consequences had begun. There is a simple, inviolable formula that every student of physics learns. Density equals mass divided by volume. It is the measure of an object's substance. And it was this calculation, this final simple piece of arithmetic, that broke modern astronomy. When they divided the impossibly low mass by the undeniably enormous volume, the result was a number that did not belong in the catalogue of the cosmos. The inferred density of 3I, Atlas, was a mere fraction of the density of water. It was less dense than freshly fallen snow. It was less dense than cork. For an object kilometers wide, an object that held itself together against the tidal forces of the sun and its own rotation, this was not just an anomaly, it was a paradox. It was a violation. Think of what this means. Nature does not build mountains out of smoke. A natural object on this scale, an asteroid, a comet, is forged from rock and ice metals and silicates. Even the most porous, loosely packed rubble pile asteroid has a density that is orders of magnitude higher. A natural object with a density this low would be a fluffy aggregate, a cosmic dust bunny of unimaginable size. But such a fragile structure would have been torn to shreds the moment it entered our solar system. Its own rotation would have flung it apart into a cloud of dust. Yet 3I, Atlas, was solid. It was coherent. It reflected light from a defined surface. It tumbled through space like a solid, rigid body. The contradiction was absolute, the cognitive dissonance overwhelming. It had the volume of a mountain but the mass of a skyscraper. It was solid, yet it was lighter than air. In conference rooms and laboratories, a frantic search began for any explanation, no matter how exotic, that did not break the known laws of physics. Could it be a solid foam of some unknown ultralight element? No known element or compound could form a stable structure of this size, with such a low density. Could it be an agglomeration of organic dust, like a colossal dandelion seed? The spectral analysis showed no evidence of complex organics, and again, the issue of structural integrity was insurmountable. Every natural avenue they explored led to a dead end, a contradiction with the observed facts. The silence in the astronomical community was deafening. The results were so bizarre, so paradigm-shattering, that for weeks no one dared to publish. They were checking their work and checking it again, haunted by the fear of some simple, embarrassing mistake. But there was no mistake. The data was sound. The mathematics was correct. The conclusion was inescapable. And so we were backed into a corner, forced by the relentless logic of our own observations to confront an idea that had, until that moment, belonged only to the speculative realms of science fiction. There is only one way to reconcile all the data. There is only one way for an object to be that large, that rigid, and yet possess so little mass. The mass cannot be distributed throughout its volume. It must be concentrated somewhere else. If the object is not a solid body of impossibly low density, then it must be something else entirely. The most parsimonious explanation, the one that violates no laws of physics and elegantly resolves every single contradiction. The lack of gravity, the solid surface, the extreme acceleration, is that 3I, Atlas, is not a solid object at all. It is a shell, The reason it has the volume of a mountain, but the mass of a building, is because all of its mass is times the building in the outer structure. The inside is empty. The hypothesis, whispered at first, then spoken with a growing, terrifying confidence at virtual meetings and encrypted chats, was that our visitor was hollow, not porous like a sponge, but hollow like a bottle, a thin, rigid outer hull, encasing a vast, empty interior. This single radical idea resolved everything at a stroke. A hollow object would have an enormous surface area for its tiny mass, allowing sunlight to push it to accelerate it just as we observed. A hollow object would be a gravitational ghost passing through the solar system while barely registering on our instruments. And a hollow object, if constructed from a strong enough material, could easily maintain its structural integrity, explaining its solid, coherent nature. The hollow inside hypothesis was no longer a wild fantasy. It had become the most conservative, the most rational, the most scientifically sound explanation on the table. It was the destination to which the data had led us, a place so far beyond our expectations that it felt like madness. But the numbers did not lie. The shockwave of this realization is still propagating. It forces us to reevaluate everything we thought we knew about what is possible in the universe. Interstellar space, we had assumed, was populated by the debris of nature, the rocks and icebergs cast off from the formation of other solar systems. But this was not debris. Nature doesn't build hollow spheres kilometers wide. The implications are so profound, so utterly transformative, that we can barely begin to grasp them. We are no longer just looking at a curious visitor from another star. We are confronting an artifact. The conversation has shifted from the pages of academic journals on celestial mechanics to the most fundamental questions a species can ask itself. For if 3I Atlas is indeed hollow, then that implies something that science has long speculated about but never before seen evidence of. It implies intent, it implies design, and it leaves us standing before the most awesome and terrifying question of all. If it was built, who or what were the builders? That single data point, that impossibly low number, did not just land in the scientific community, it detonated. The initial hushed excitement of discovery was instantly consumed by an intellectual firestorm. For the men and women who had dedicated their lives to the clockwork elegance of the cosmos, the conclusion was not merely radical, it was a violation. A number so divorced from reality it felt like a prank played by the universe itself. And so the first line of defense was erected, a firewall of professional skepticism built from mathematics and merciless scrutiny. The calculations were not just rechecked, they were torn apart atom by independent teams across the globe. Rival institutions, normally competing for funding and prestige, now shared every scrap of their work. They hunted for the phantom decimal point, the misplaced variable, the subtle flaw in logic that would restore order. They ran the orbital mechanics through supercomputer simulations, projecting its path backwards and forwards through 1,000,000 years of gravitational chaos, searching for any perturbation, any resonance, any interaction we might have missed that could account for the anomaly. They fed the raw telemetry from the observatories into entirely different software suites, coded by different hands, governed by different philosophies, all in a desperate search for a bug in the original machine. Every search came back empty. Every calculation, no matter how it was tortured, yielded the same ghost. A mass so negligible it made a mockery of the object's immense size. The math, it seemed, was sound, unforgivingly, terrifyingly sound. If the answer wasn't a mistake in our logic, then perhaps it was a mistake in our perception. The entire premise rested on two pillars: the object's observed trajectory, which gave us its gravitational interaction, and thus its mass, and its observed brightness, which combined with its distance gave us its size. The mass calculation had survived the initial onslaught. Now the scrutiny turned, with a vengeance, to the other pillar, its apparent size. Had we misjudged its dimensions? Could 3I Atlas be a cosmic mirage, a trick of light and distance? The first most obvious explanation was that it wasn't a single solid object at all. Perhaps we were looking at a vast, yet exceptionally diffuse cloud of dust and ice. A swarm of smaller bodies flying in such tight formation that from our immense distance they appeared as one continuous surface. This was a comfortable idea, a familiar one. We had seen comet nuclei disintegrate, creating ghostly shrouds of debris. But this hypothesis crumbled under the cold, hard glare of the photometer. The light reflecting from Atlas was too stable, too uniform. A cloud of disconnected particles would twinkle its brightness, fluctuating chaotically as its individual members tumbled and turned in the sunlight. Yet the light curve of this interstellar visitor was smooth, rhythmic, displaying the consistent repeating pattern of a single coherent body rotating on a stable axis. It did not behave like a cloud. It did not behave like a swarm. It behaved like one thing. And so, with the simplest rebuttals exhausted, the community was forced into more exotic territory. The battle for a natural explanation had truly begun. If it was indeed a single object, the only way to reconcile its volume with its mass was to propose a structure of almost unimaginable porosity. Not just a rock with holes, but a solid that was almost entirely whole. Imagine a cosmic sponge, an object where 99.9% of its internal volume is empty space. A structure more ephemeral than smoke, yet somehow holding itself together across millions of kilometers of unforgiving vacuum. The material scientists and geophysicists stepped forward, their models growing stranger by the day. They proposed a celestial aerogel, a substance spun from filaments of carbon and silicate dust frozen together at temperatures just shy of absolute zero. In laboratories on Earth, we can create aerogels, ethereal solids, so light they can be balanced on the petals of a flower. Could the universe, in the cold, dark nurseries between the stars, manufacture such a thing on a scale of kilometers? For a moment, this theory seemed to hold a desperate promise. It could, in principle, account for the density. It provided a framework, however fragile, to understand what we were seeing. You could envision it a ghostly lattice of frozen black threads, a kilometer-wide crystal of nothingness tumbling silently through the dark. But the more they modeled it, the more this beautiful, fragile idea began to tear itself apart. Such a structure would be catastrophically weak. The slightest gravitational stress, the gentle tidal forces exerted by its passage near Jupiter, or even the Sun, should have flexed it, cracked it, and reduced it to a glittering puff of cosmic dust. Its own rotation, the very spin that gave us its consistent light curve, would generate centrifugal forces that its delicate web-like structure simply could not withstand. The numbers refused to cooperate, to be strong enough to survive its journey into our solar system, and especially its hairpin turn around our star. This cosmic foam would need to be made of something far stronger than any known frozen dust. It would require a material with an unprecedented, almost magical strength-to-weight ratio. The theory collapsed under a fundamental contradiction. It had to be light enough to explain the mass, yet impossibly strong to explain its own survival. The cosmic sponge was squeezed dry of its explanatory power. With porosity failing, another related idea was put on the table. Perhaps it wasn't a single contiguous foam, but what astronomers call a fluffy aggregate. Think of it not as a sponge, but as a cosmic dust bunny. A gargantuan, loosely packed ball of pebbles and ice barely held together by their own minuscule gravity and perhaps some faint electrostatic charge. This model had a certain appeal. The interstellar medium is full of dust and small grains. It wasn't a stretch to imagine these particles slowly, gently clumping together over billions of years in the deep cold. This object wouldn't need exotic physics or unknown materials, just time and the gentle accumulation of primordial stuff. It would be like the universe's largest, most fragile snowball. But this idea too was plagued by the specter of its own fragility. A fluffy aggregate is by its very nature on the verge of disintegration at all times. How could such a delicate construction survive the violent shocks of its own birth? How could it hold its shape after being ejected from its home star system, a process that is invariably chaotic and destructive? And how, after a journey of millions of years, could it arrive here perfectly intact, spinning like a top? We ran the simulations again. We modeled a kilometer-wide ball of fluff making its journey toward our sun. In every plausible scenario, the outcome was the same. Long before it reached the orbit of Mars, the gentle, persistent pull of the sun's gravity would begin to stretch it. Tidal forces would knead it, pulling the near side more strongly than the far side. The fragile bonds holding the aggregate together would snap. It wouldn't arrive as a single object. It would arrive as a long, drawn-out smear of dust and debris, its constituent parts liberated into their own independent orbits. What we saw was not a smear. What we saw was a single sharp point of light holding its form with disciplined integrity. The cosmic dust bunny was swept away. Each failed explanation only deepened the chill. The intellectual vertigo was setting in. The community had thrown its best conventional ideas at the problem, and the problem had thrown them back unbroken. This is a critical juncture in the scientific process, the moment when you must turn your skepticism inward. You must question not just the phenomenon, but the very tools you are using to perceive it. The focus now shifted to a far more uncomfortable possibility, a systematic error, a subtle flaw not in our logic but in our instruments. Something that had been staring us in the face all along, invisible because it was part of the very lens through which we were looking. This phase of the investigation was the most grueling. It involved a painstaking global audit of the very foundations of modern observational astronomy. Teams were dispatched to the great mountaintop observatories. They didn't just recalibrate the telescopes, they disassembled key components. They tested the quantum efficiency of the digital sensors, pixel by pixel, searching for any subtle non-linearity that might make a faint object appear artificially large and well-defined. They remeasured the precise spectral transmission of the atmospheric column above each observatory, looking for any undiscovered absorption line, any pocket of aerosolized dust or ice crystals that could be scattering the light from Atlas in a deceptive way. The software that processed the raw photons from these telescopes was subjected to an unprecedented level of scrutiny. Programmers who had written the code years ago were called back to defend every line. Could the algorithms that correct for atmospheric turbulence, the very ones that allow us to see sharp images, be introducing a subtle smearing effect on this specific type of object, making it look bigger than it was? They created artificial stars in their computer models, simulated their light passing through a virtual atmosphere, and fed them into the software, trying to trick it, to force it to make the same mistake. But the systems were robust, the corrections were accurate, the data, raw and unforgiving, remained unchanged. The ghost was not in the machine. The search for error grew more desperate, venturing into the truly esoteric. Could a subtle gravitational mirage be at play? Einstein's theory of relativity tells us that mass bends space-time and therefore bends the path of light. This phenomenon, gravitational lensing, is usually only significant around massive objects, like galaxies or black holes. But could there be a small dark object, a rogue planet, or a primordial black hole positioned perfectly along our line of sight to 3i, Atlas? Could such an object be acting like a cosmic magnifying glass, distorting the light from the interloper and making it appear deceptively large? If so, its real size would be smaller, and its density, while still low, might just fall back into the realm of the plausible. Astronomers scanned the star fields around Atlas's trajectory with fanatical intensity. They were hunting for the telltale signs of a lensing event, a slight distortion in the shape of background galaxies, or a brief symmetrical brightening as the unseen object passed by. The search encompassed terabytes of archival data from sky surveys conducted years earlier. They were looking for a gravitational needle in a cosmic haystack, but the space around the object's path was clean. The background galaxies were pristine and undistorted. There was no hidden lens. There was no mirage. The image we were seeing was true. One last bastion of natural explanation remained. It was the most stubborn, the most difficult to disprove, and it centered on the one force we couldn't entirely account for: outgassing. We see this with every comet. As it nears the sun, its icy surface heats up and sublimates, venting jets of gas and dust into space. These jets act like tiny rocket thrusters, imparting a gentle, non-gravitational force that alters the comet's path. Our mass calculation for 3I, Atlas, was based purely on its gravitational trajectory. If there were other forces at play, forces we couldn't see, then our entire calculation was built on a false premise. What if this object was venting a type of gas that was completely invisible to our instruments, something that didn't glow or reflect sunlight like pure hydrogen or methane? If it was spewing these stealth jets, it could be pushing itself around the solar system, subtly altering its orbit in a way that mimicked the pull of a much more massive object. It might not be absurdly light at all. It could be a perfectly normal, dense, rocky body whose true mass was being masked by this unseen propulsion. This was the final hope for a return to normalcy. To test it, we couldn't just look for a visible coma. We had to look for the gas itself. The world's most powerful spectrographs were trained on that single point of light, breaking it down color by color into a barcode of its chemical constituents. They were searching for the faintest absorption or emission lines, the telltale chemical fingerprints of any gas surrounding the object. The great radio telescopes, dishes the size of football fields, listened for the faint hiss of molecular transitions. The most sensitive infrared cameras, cooled to near absolute zero, stared at it, hunting for the slightest whisper of waste heat that any venting process, no matter how efficient, must produce. They saw nothing. The spectrum was clean. The radio frequencies were silent. The infrared signature was that of a cold, inert body, reflecting only the distant light of the sun. There were no jets. There was no stealth propulsion. There was no outgassing. There was no cloud. There was no cosmic sponge. There was no fluffy aggregate. There was no error in the math. There was no flaw in the instruments. There was no mirage. One by one, with the full systematic rigor of the global scientific endeavor, every single portcullis leading back to the known world had been slammed shut. We were trapped in the throne room with the impossible king. The attempts to falsify the hollow hypothesis had failed. And in the unforgiving logic of science, a hypothesis that repeatedly withstands every attempt at falsification, no matter how bizarre it may seem, becomes progressively stronger. The scientific community stood at a precipice, a place it had not been for a century. Every rational, natural, and even wildly speculative explanation had been pursued to its bitter end, and all that remained was the original terrifying number. A conclusion so profound, so utterly alien, that it seemed to mock the very laws we thought governed the universe. We had followed the evidence, and it had led us over a cliff. Now, suspended in the abyss of uncertainty, we were finally forced to look down and confront the question that had been lurking in the shadows all along. If 3I, Atlas, was not a product of nature, then what was it? And so we were left teetering on a precipice of understanding. On one side lay everything we thought we knew about the cosmos, the predictable physics of asteroids, the chaotic but understandable nature of comets, the solid, dependable reality of rock and ice sculpted by gravity and time. On the other side was 3I, Atlas, a gravitational ghost, an object whose trajectory whispered of a density so impossibly low that our models screamed in protest. It moved with the gravitational footprint of a feather, yet it possessed the dimensions of a mountain. Every calculation we had made, every photon we had collected, only served to deepen the paradox, stretching the fabric of known astrophysics to its absolute breaking point. The debate raged not just in academic journals but in late-night laboratory sessions and hushed conference corridors. Was it a new type of cosmic fractal? An ultra-porous agglomeration of dust barely holding itself together? Or was there a fundamental error in our observations? A subtle miscalculation, somewhere in the chain of logic that would bring this anomaly back into the fold of the familiar. For months, the stalemate held. Two camps entrenched, unable to reconcile the object's path through space with its apparent physical presence. A new kind of evidence was needed. Not just another measurement of its position or another spectrum of its reflected light, but something more intimate, more revealing. We needed to ask the object a different question entirely. We needed to listen not just to where it was going, but to how it was, times feeling, times the journey. The breakthrough would not come from the world's largest optical telescopes, nor from the powerful radio dishes that listen for whispers from the dawn of time. It came instead from a novel and exquisitely sensitive technique, a network of instruments scattered across the globe, working in perfect unison. They called it gravitational oscillation interferometry. It was not designed to take a picture. Its purpose was far more profound. By combining the light from multiple telescopes, separated by thousands of kilometers, this planetary-scale instrument could detect infinitesimal shifts in an object's rotation. It could measure a wobble so subtle it was akin to discerning the flutter of a single falling leaf from the distance of the moon. For the first time, we had the ability to see how 3I, Atlas, was spinning on its axis as it tumbled through the void. This was the key. Any rotating object in space, whether a planet or a pebble, is subject to the complex gravitational tides of the solar system. The immense pull of the sun and the gentle but persistent nudges from planets like Jupiter exert a torque, a twisting force on it. For a solid uniform object, like an ordinary asteroid, this results in a slow, predictable, and well-understood gyroscopic precession. A steady, rhythmic wobble, like a spinning top, gracefully slowing down. This was the baseline, the expected signature. The observation campaign was an exercise in extreme patience. For 127 nights, as Earth turned, different observatories would pick up the vigil, their instruments locking onto the faint star-like point of 3I, Atlas. They measured the polarization of its reflected sunlight, searching for the repeating pattern that would betray its spin. The data streamed in terabytes of information, a torrent of numbers that held the secret of the object's true nature. In a darkened control room in the Atacama Desert, the initial results began to paint a picture on the screen. And it was a picture of utter chaos. The signal was there, but it was not the clean, elegant sine wave of a simple precession. It was a complex, jagged, almost organic rhythm. There was the primary spin, a slow rotation every 19 hours, but superimposed on that was a faster, more frantic vibration, a shiver that ran through the object. And beneath that, an even deeper, slower oscillation, a resonant hum that seemed to make the entire structure thrum like a plucked string. It was unlike anything ever seen before. The team's first reaction was disbelief, followed by a frantic search for error. Was it atmospheric interference? Was there a flaw in the calibration of the instruments? They cross-referenced data from different sites from different nights, running diagnostic after diagnostic, but the signal remained. It was real. The object was not just wobbling, it was ringing. It was vibrating in a complex harmony of frequencies, a celestial tuning fork struck by the invisible hammers of planetary gravity. For weeks, the meaning of this cosmic symphony eluded everyone. The world's finest minds in orbital mechanics stared at the data, their models failing one after another. A solid body, no matter its shape or composition, could not produce these harmonics. A loose rubble pile would simply be torn apart by such complex stresses. The answer, when it finally came, did not arrive in a flash of insight, but through the painstaking process of elimination, led by a young postdoctoral researcher who decided to input a parameter so outlandish, so contrary to all natural expectation that it had been dismissed as science fiction. She modeled 3I, Atlas, not as a solid object, but as a thin, rigid shell. Imagine holding a solid steel ball in your hand. If you tap it, it emits a simple high-pitched ping. The sound is short, uncomplicated. The energy dissipates quickly through its dense uniform structure. Now imagine holding a delicate hollow glass ornament. If you tap that, the sound is entirely different. It produces a complex ringing tone, a chorus of overtones and harmonics that resonates and lingers. The hollow structure allows the vibrational energy to propagate, to reflect off the inner surfaces, to create standing waves. The ornament doesn't just ping, it sings. This was the conceptual leap that unlocked the puzzle of 3I, Atlas. The gravitational tides of the solar system were tapping the object as it flew past. A solid body would have responded with a simple, predictable precession, a clean ping. But what the team was observing was not a ping. It was a lingering, complex, resonant song. The data was the sound of a hollow object singing in the vacuum of space. The researcher and her team worked feverishly building a new computer model. They defined an object with the precise dimensions of 3I, Atlas, a vast, elongated shape hundreds of meters long. They gave it the total mass derived from its trajectory, the incredibly low mass that had started the whole mystery. But instead of distributing that mass evenly throughout its volume, they concentrated it entirely in a thin outer shell, leaving the inside almost completely empty. The shell's thickness in their model was astonishingly slight, perhaps only a few meters, constructed of a material with immense tensile strength. Then they placed this virtual object into a simulation of our solar system and let it run. The results that came back were breathtaking. The virtual hollow object began to spin and tumble, subjected to the same gravitational forces as the real 3I, Atlas. And on the screen, a graph began to form, plotting the model's predicted rotational oscillations. It was a jagged, complex waveform, a beautiful and intricate pattern of resonant frequencies. The team then overlaid the graph of the real data, the signal painstakingly collected by the Global Telescope Array. The two lines, one from a purely theoretical model of a hollow shell, and the other from a real object millions of kilometers away in the dark, traced over one another. They were not just similar, they were a perfect, undeniable, electrifying match. Every peak, every trough, every subtle harmonic vibration that had so baffled them was perfectly replicated. The frantic shiver, the deeper, resonant hum, it was all there. It was the eureka moment on a planetary scale, a discovery so profound it felt like a violation of natural law. A collective silence fell over the control room, the kind of silence that follows a revelation that changes the world. They had found it, the smoking gun, the incontrovertible mathematical proof. 3I, Atlas, was hollow. The implications cascaded outwards, tearing down decades of established astronomical certainty. A natural object could not form this way. A loose conglomeration of ice and dust, an asteroid, a comet. These are objects built by the gentle, persistent accumulation of matter under gravity. They are rubble piles, or solid chunks, or porous snowballs. The universe does not build vast, empty, rigid shells with the structural integrity of a warship's hull. The physics required to do so naturally simply does not exist. The pressure and temperature gradients needed to forge such a structure and then evacuate its interior belong to the realm of fantasy. It would be like finding a perfectly machined pocket watch on a deserted beach. The object itself screams of a process, of a purpose that nature cannot provide. The scientific consensus, that slow-moving, deeply conservative beast, began to turn. The initial reaction from the wider community was predictably one of profound skepticism. The data was challenged, the methodology was scrutinized, with a ferocity reserved for only the most paradigm-shattering claims. Competing teams around the world ran their own analyses, desperate to find the flaw, the subtle error that would restore order to their universe. But there was no flaw. The signal was unambiguous. The mathematics was sound. One by one, the titans of the field, the elder statesmen of planetary science, were forced to confront the impossible. We can picture them now, standing before whiteboards covered in elegant equations that had described the cosmos for a century, equations that now felt obsolete. The uncomfortable, terrifying, exhilarating conclusion became inescapable. The structure of 3I Atlas was not a product of random celestial mechanics. To accept the data was to accept that this object, tumbling silently through our solar system, was fundamentally different from anything humanity had ever encountered. It was a manufactured thing, an artifact. The conversation shifted from the language of geology and astrophysics to a new, more hesitant vocabulary, one laced with engineering and design. The shell itself had to be made of a material of unimaginable strength to withstand the stresses of its own rotation and the tidal forces of the sun without fracturing. Spectroscopic analysis, revisited in light of this new structural model, began to make a terrifying kind of sense. The strange, non-reflective surface, the unusual thermal inertia. These were not the properties of a dusty rock, but perhaps of a weathered exotic alloy or a ceramic composite. We were no longer looking at a celestial body. We were looking at a vessel, a relic, a piece of technology so ancient its surface has been pitted and scarred by eons of micrometeoroid impacts, yet so robust its fundamental structure remains intact. The discovery did not answer the great question. It fractured it into 1,000 more. Who built it, and for what purpose? Was it a ship designed to carry occupants across the interstellar gulf? If so, where were they? Was the vessel derelict, a ghost ship on an eternal silent voyage? Or was it something else entirely? A probe, a marker, a piece of cosmic art? Perhaps it was a Bracewell probe, a silent, autonomous sentinel, designed to watch, to listen, and to wait for a nascent intelligence like ours to finally reach for the stars and notice its subtle, anomalous passage. Or perhaps its purpose is something our minds, conditioned by the gravity and biology of a single world, are not yet equipped to even conceive. The very emptiness of its core became the most profound statement. The hollow space was a declaration. It was a space for something, a volume defined by a boundary. It was the difference between a rock and a bottle. A rock simply times is asterisk. A bottle is times for times something. It is designed to contain, to protect, to transport. 3I Atlas was a bottle, and we had just found it floating in the cosmic ocean. Its message, if it ever held one, long since gone, or perhaps waiting for us to figure out how to open it. This was the turning point. The moment the human story became entangled with a mystery far older and grander than itself. We had proven the times what, asterisk. 3I Atlas is a hollow, artificial construction. This fact was now as certain as the existence of Jupiter or the rings of Saturn. But in solving that puzzle, we had unleashed a far greater one, a question that would now hang over our civilization, over our art, our science, our religions. The question of times, who asterisk. We were no longer just looking at an astronomical curiosity. We were staring at our own reflection in a dark, silent, alien mirror. And the universe suddenly felt infinitely larger and infinitely more lonely. The era of comfortable certainty was over. A new era, one of profound and unsettling wonder, had just begun. And so we are left here in the quiet aftermath of a revelation, left staring at the ghost of a trajectory, a faint line drawn across the celestial sphere by an object that defied every category we had meticulously constructed for the heavens. We began this journey with a flicker of light, a single anomalous pixel flagged by an algorithm in the dead of night. It was a discovery like so many others, a brief flare of excitement in the endless, patient work of watching the sky. We named it 3I Atlas, the third interstellar visitor. And we prepared our standard playbook for cosmic passers-by. We expected a comet shedding its ancient ice in a glorious tail, or perhaps a dense rocky shard like Oumuamua before it, a messenger from a star system born of the same familiar physics. What we found instead has driven a fissure through the very bedrock of our cosmic understanding, forcing us to confront a possibility so profound it borders on the sacred or the terrifying. The story of 3I, Atlas, is not one of a simple discovery, but of a slow, creeping realization, a mystery that unfurled like a cryptic map, each new piece of data revealing a landscape more alien than the last. You have journeyed with us through the painstaking process of that revelation. You saw the first puzzling spectra, which showed a surface composition that seemed almost deliberately designed to be inert. A strange, dark material that neither reflected nor absorbed light in any way. Our models of natural space weathering could predict. It was a cosmic stealth material, a surface that hinted at an unnatural history, yet we still sought a natural explanation. Perhaps it was coated in complex tholins, organic compounds forged in the outer reaches of a bizarre protoplanetary disk. We reasoned, we rationalized, we tried to fit the enigma into the comfortable confines of established astrophysics. Then came the trajectory deviation, the subtle, inexplicable course correction that lacked any visible outgassing, any cometary jet, to explain its non-gravitational acceleration. It moved as if guided by a whisper, a force we could not see and could not measure. We exhausted the possibilities one by one. Solar radiation pressure. The calculations failed. The object was too large, too massive. Electromagnetic interaction with the solar wind, its composition and lack of a magnetosphere rendered that hypothesis untenable. Each discarded theory felt like a door closing behind us, funneling us down a corridor towards a single, unthinkable room. The final lock on that door was the gravitational lensing experiment, the desperate, brilliant use of an ancient galaxy's light to weigh our visitor as it passed. It was the ultimate arbiter, the one measurement that could not be fooled by surface chemistry or unseen forces. It measured pure mass, the object's fundamental gravitational truth, and the truth it gave us was impossible. The truth was a number that broke our science. A mass so spectacularly impossibly low for an object of its size and structural integrity that it left the world's greatest minds in a state of stunned silence. The data was irrefutable, checked and rechecked by teams across the globe, the conclusion inescapable. For 3I, Atlas to possess that volume, yet exert such a frail gravitational pull, the vast majority of its interior had to be nothing. An empty space. It was a shell. A vessel of cosmic emptiness, a structure whose density was more akin to that of aerogel than of rock or metal. It was, by every metric, our physics could provide, hollow. And with that single word, the universe we thought we knew evaporated, replaced by a cosmos infinitely more strange and filled with far deeper questions. We had spent centuries looking for life, and in the end, it was a profound and terrifying absence, a void wrapped in a thin, dark skin that screamed of intelligence. We stand now at a great fork in the road of cosmic philosophy, two paths stretching out before us into an unknown future, each one demanding a radical leap of imagination. The first path is that of unprecedented nature. It asks us to believe that the universe, in its infinite and chaotic inventiveness, can produce structures that we, in our limited experience, would mistake for artificial. Could this object be a naturally formed, fractal aggregate, a cosmic snowflake of immense scale, assembled with such delicate precision that it is mostly empty space, yet strong enough to survive the crushing tides of interstellar travel? Perhaps it is a shard of some exotic form of matter, a collapsed bubble from the quantum foam of the Big Bang, whose properties defy our current understanding of density and form. This path requires us to invent entirely new physics, to postulate materials and formation processes that exist only in the most esoteric equations. We must imagine a star system where such objects are not anomalies but common debris, where the laws of accretion and planet formation work in fundamentally different ways. It's a tantalizing prospect, suggesting that the universe is not just stranger than we imagine, but stranger than we can imagine. Yet for every natural model we construct, 3I Atlas presents a contradiction. Its structural integrity seems too high for a fragile aggregate. Its uniform inert surface seems too specific for a random cosmic shard. The path of natural explanation, while the scientifically prudent choice, feels like an uphill climb against a hurricane of improbable coincidences. It feels like we are deliberately averting our gaze from the simpler yet more staggering alternative. The second path is the one that has haunted our dreams and whispered in our myths since we first looked up. It is the path of artifice. This path suggests that 3I Atlas is exactly what it appears to be: a manufactured object, a piece of technology, a thing built with purpose and intent by a non-human intelligence. To walk this path is to step out of the familiar world of astronomy and into a new reality, one that humanity has long anticipated with a mixture of unbridled hope and existential dread. If we accept this possibility even for a moment, the questions that arise are monumental, cascading through every field of human thought. It is no longer an object, it is a statement. But what is it saying? Is it a probe? A silent, passive observer, one of perhaps billions drifting through star systems on a mission of galactic reconnaissance that has lasted for eons? Its hollow nature could be a necessity of its design, a housing for instrumentation and propulsion systems we cannot begin to fathom, all protected by a hull built to endure millions of years of cosmic radiation. It passed us by without a signal, without any attempt at communication, perhaps because we were not its primary objective, or more chillingly because its mission was simply to watch and to report back to its creators that this small blue world was now home to a species that could finally see it for what it was, a species that had at last developed the technology to notice the ghost in its own backyard. Or could it be something else, not a probe, but a vessel, a ship, an ark? The vast, empty space within, not for machinery, but for something else. Life, or the memory of life. Perhaps it is a derelict, its crew long dead, its original purpose lost to the ages. Now just a silent tombstone tumbling through the void, the last remnant of a civilization that vanished before life on Earth had even crawled out of the oceans. The thought is both tragic and magnificent, to encounter the grand and silent legacy of another's story, a final beautiful piece of cosmic archaeology. Or perhaps it is not a tomb but a seed, a Brasero probe carrying the building blocks of life, or the digital consciousness of a species waiting for the right conditions to take root in a new and fertile star system. Was its flyby of our sun a test of our system's potential? A gravitational nudge onto a new course toward a more promising stellar nursery? We may never know. Then there is the final, most disquieting possibility. What if 3I Atlas is not a relic of the past, but a harbinger of the future? What if it is a marker, a celestial buoy, placed in a deliberate orbit to be eventually discovered? A sentinel designed to remain inert and unremarkable until a system's native species achieves a certain level of technological sophistication, the level required to accurately measure its impossible mass. In this scenario, our discovery was not an accident, it was a trigger. The moment we understood its hollowness, we tripped a cosmic wire announcing our presence on the galactic stage. We have in effect answered a question we didn't even know was being asked, and we now wait in the silence that follows, wondering if that answer will elicit a response. The emptiness of 3I Atlas, may not have been a physical void, but a metaphysical one, a question mark, hung in the darkness of our own solar system. Regardless of which path proves to be the truth, the legacy of 3I, Atlas, is already written. It is a catalyst. It has fundamentally and permanently altered our relationship with the cosmos. The discovery has injected a profound sense of urgency and purpose into our celestial endeavors. Observatories are being redesigned, search algorithms rewritten. We are no longer just looking for planets or listening for signals. We are now actively hunting for anomalies, for artifacts, for things that times should not be there. The search for extraterrestrial intelligence SETI has undergone a paradigm shift. For decades, it was an endeavor of passive listening. Our radio telescopes, like ears pressed against a wall hoping to overhear a distant conversation. Now it must also become a program of active archaeology. We must scan the sky for the silent physical evidence of technology, for the gravitational and spectroscopic signatures of things that nature alone cannot build. 3I, Atlas has handed us a new mandate for exploration. It is no longer enough to send robotic probes to Mars or the moons of Jupiter. The scale of our ambition must now match the scale of this mystery. We must develop technologies that can not only observe such objects from afar, but can actively intercept them. We need to build a new generation of interstellar spacecraft probes, capable of achieving a significant fraction of the speed of light, ready to be launched at a moment's notice to chase down the next visitor that passes through our home. This is a generational challenge, perhaps a centuries-long endeavor, but it is a challenge we can no longer ignore. The question of whether we are alone has been transformed. It is no longer a philosophical debate. It is an engineering problem. The evidence may already be in our solar system, waiting to be found. We have, in a sense, been awakened from a long slumber. We have spent centuries cataloging the natural wonders of the universe, the majestic spin of galaxies, the violent birth and death of stars, the intricate dance of planets. We built a beautiful, coherent model of a cosmos governed by elegant, impersonal laws. We saw ourselves as its sole observers, the only minds capable of appreciating its grandeur. 3I Atlas suggests that this may have been a profound and arrogant assumption. It hints that the universe is not just a stage for physics and chemistry, but may also contain other actors, other minds, other stories, unfolding on a scale we can barely comprehend. It tells us that our cosmic loneliness might be a choice, a consequence of not looking in the right way or with the right tools. As we conclude our journey, the object itself is now receding, growing fainter with every passing hour. It is tumbling back into the great silent darkness from which it came, its secrets intact. It gave us no answers. Instead, it left us with a gift of far greater value, a perfect and enduring question. It has rekindled the fire of human curiosity, the primal urge to explore, to know, and to understand what lies beyond the horizon. It has forced us to look at the familiar night sky with new eyes, to see it not as a static backdrop of predictable orbits, but as a dynamic living space, a cosmic ocean through which unknown vessels might be sailing. Its passage was a reminder that we are still in the infancy of our cosmic awareness, standing on the shore of an ocean of possibilities, having collected only a few smooth stones of knowledge, while the vast sea of truth lies undiscovered before us. The silence it leaves in its wake is now filled with our own imagination, with new dreams of discovery and new fears of the unknown. It is a silence that beckons us forward. Whether 3I Atlas was a miracle of nature or a whisper from another mind, its message is the same. It tells us to keep watching the skies, to keep searching, to keep pushing ourselves to the very edge of what is possible, because the universe is not empty. It is full of wonders we have not yet earned the right to understand, and we now know with a certainty that is both thrilling and deeply humbling that the next great discovery, the one that changes everything forever, may not be a distant star or a new kind of particle. It may be a direct encounter with the thoughts of another, an artifact of alien hands, a ghost that proves once and for all that we are not alone. The journey to find it has just begun.